Differentiability. First, I would like to recall the definition of f prime of c, or the derivative of the function f(x) at x equals c. It is the limit of f of c plus h minus fc over h when h approaches 0 if the limit exists and is finite. So I see here two conditions. If the limit does not exist or is infinite, then the function f(x) has no derivative at x equals c. Definition. A function f is differentiable at x equals c if the derivative of the function at x equals c exists. This means that this limit of fc plus h minus fc over h when h approaches 0 exists and finite. It means that the answer for is the limit exist is yes, and the answer for is this limit finite is also yes. In the previous section, we found that the derivative of the function f(x) equals square root of x is 1 over 2 square root of x, and we also found out that the derivative of the function at x equals 25 is 1 over 10. This means that the function f(x) equals square root of x is differentiable at x equals 25. Moreover, for every finite number that is more than 0, the derivative, which is 1 over 2 square root of x, is a finite number. This means that f(x) is differentiable for any value of x which is larger than 0. Definition. A function f is differentiable on the interval ab if it is differentiable on any value between a and b. And another definition, a function f is differentiable everywhere if it is differentiable to all values of x, which means on the interval negative infinity to infinity. Theorem. If f is differentiable at x equals c, then it is continuous at x equals c. I would like to recall a previous theorem. If a function is continuous at x equals c, then the limit of the function when x approaches c exists. We can summarize both together, and we get that if f is differentiable at x equals c, then it is continuous at x equals c. But also, this implies that the limit at x equals c exists. But also, if the limit does not exist, then it is not continuous. But if f is not continuous, this implies that it's not differentiable at x equals c. Let's recall again the definition of a differentiable function at a point x equals c. There are actually two conditions here. First of all, the limit f of c plus h minus fc over h when h approaches 0 has to first exist and it must be finite. We can conclude from here that if a function is continuous and not differentiable, then something wrong with those two conditions of this limit to exist or to be finite. In case 1, it is possible that this is infinite. But this also means that the slope of the function at x equals c is vertical. Let's see such an example. If you observe this function, you can easily see that when x equals 2, the tangent line to the graph of the function is vertical. It means that it's not differentiable at x equals 2. Here is another case, case 2. This limit just does not exist as a limit. And here's an example. Let's take the function absolute value of x and observe what happens at x equals 0. Here's the derivative of the function at 0. It's the limit of f of 0 plus h minus f of 0 over h when h approaches 0. We are substituting absolute value for the function, and we get that this is the limit of absolute value of 0 plus h minus absolute value of 0 over h when h approaches 0. This is then the limit of absolute value of h over h when h approaches 0. We have to take the two-sided limit and to do 1, 2, 3. Absolute value of h is itself if h is greater or equals to 0, and it's the opposite, which means negative h if h is less than 0. Now let's do 1, 2, 3. The limit from the right of this function h in absolute value over h is now going to be 1 because absolute value of h is replaced by h. And the limit from the left is negative 1. So we get that the limit at 0 itself does not exist. And we can conclude that this function is not differentiable at x equals 0. Let's now observe the graph of this function. This is the graph of y equals absolute value of x. You can see the sharp corner and you can see immediately that the function is not differentiable at x equals 0. But even more, the slope here is 1 and the slope here is negative 1. So clearly, the derivative of this function is 1 if x is more than 0 and negative 1 if x is less than 0. But at 0 itself, it's not differentiable. But this also shows that the function is differentiable for any value of x except x equals 0. We can summarize that the function f is not differentiable at c if the graph of f has a horizontal tangent line at x equals c, or that the graph of f has a corner at x equals c. This is in the cases at which f is continuous at x equals c. But also, a function that it's not continuous at x equals c is obviously also not differentiable at x equals c. In case 3, we have few cases. Those are all the cases for which f is discontinuous at x equals c. One of them can be that c is not in the domain of the function. The limit from the right maybe does not exist. The limit from the left maybe does not exist. Maybe both-sided limit exists, but they are not equal. Or there is a limit, but the limit does not equal to the value of the function at c. We are now ready to inspect graphs for differentiability. And here's an example. We are going to fill in the chart. We will ask if the function is differentiable for each one of those values of the x's and give a good reason why not, if it's not. At x equals negative 5, the function is continuous, and that's why I only have to make sure that there is no sharp corner and there is no tangent line which is vertical. And because I don't have those two, it is differentiable at x equals negative 5. What about x equals negative 2? I see a corner. What about -1? Clearly not. The function is even not continuous there. The reason for this function to be not continuous there is because the limit from the left is not equal to the limit from the right. At x equals 3, it's not differentiable because it's not continuous. The limit exists but is not equal to f of c. 6, the answer is again no because we have a sharp corner. At 10, the function is differentiable because there is nothing that suggests otherwise.